Thank you, Gerard. Back to English, sorry. So thank you for giving this opportunity to talk today about elastic circuit. Most of this work I'm going to present has been done in collaboration with some colleagues, Mike Kishinevsky and Mark Galceran. And let me review a little bit what we mean by elasticity. So last week I talked about asynchronous circuits, and what I meant by time elasticity was that we could adapt time to the operating conditions, to the operations that we are doing, and we could, for example, stretch and shrink the cycle time and accommodate to these requirements. Okay? So today I'm going to talk about elastic circuits as a generalization of that, in which I will show that we can adapt time even having clock or without clock. In both cases, we can have elasticity. So let's review a little bit what is a synchronous circuit. And again, we have a clock generator that is delivering pulses to the sequential elements, the flip-flops or the registers in the system. And this clock generator has to work at a certain frequency. This frequency determines a cycle period, and the cycle period must be always longer than the critical path in the circuit. That's the main timing constraints when defining the frequency of the system. On the other hand, in a synchronous circuit, this is adaptable. So we have a ring oscillator that is generating the pulses to these latches. There is some delays that are matched with the delays of the combinational logic. And again, the frequency of this ring oscillator should be longer than the critical path. But here we have the possibility to adapt to the operating conditions. So we may change temperature, voltage, and this ring oscillator would adapt automatically. We can also adapt to the different delays in the operations. And remember a little bit the rules of transferring data from one stage to the other. So basically, if we have a pipeline, what we need is when we have valid data at the input of one stage and some empty space at the output, then we can transfer data. And all this is done through local handshakes. So we don't have a global clock. We have just local handshakes based on bidirectional signals we call request acknowledge. And for example, here we can send dynamically and in parallel things from one stage to the other, based also always on these rules in which we need valid data on one side, a space on the other side, and that makes that these two inputs of the C elements are active and we can trigger them, okay? So basically that's the way synchronous and asynchronous circuits work. Now let's try to mix these two walls and do something else with them. And I would like to start talking about a paradigm that has been used very often recently, which is GALS, which means globally asynchronous, locally synchronous. What is that? I mean, in our complex designs today, we have different IPs, okay, components, that do different operations, and the nature of those operations are different. So, and that means basically that not necessarily we need the same clock frequency in all of them. One of them is a microprocessor, the other ESP, image processing, maybe slow peripherals. So why do we need the same frequency? Even some of these components may have variable latencies. The memory, for example, may deliver your data sometimes in a couple of cycles, sometimes in 30 cycles, right? So we need to combine different clock domains. And between these clock domains, we have sometimes what we call bridges, like here. We need to be interfaces between different clock domains and some logic, some interfaces that are called clock domain crossing. And I would like to talk a little bit about what this means. So there are different ways of putting different clock domains in a system. For example, one of them is to have only one clock generator, and this clock generator delivers the clock to different components, but maybe the clock skew is not totally exact, okay? There is some skew between them. So that means that maybe there is some skew that we can calculate at design time, and still we have a common reference point that allows us to transfer data between one component to the other component in a reliable way. The frequency is exactly the same because the clock generator is the same. Another variation is that we have one master clock generator, and then we have different frequencies, and these different frequencies are generated, for example, by dividers. So we may have that one component has half of the frequency of the other component, or 1/4, or 2/3. So there is a rational relationship. And the good thing about this is that we can always find just some instance in time in which we know that the clock edges are aligned, and we can do a reliable data transfer. Okay? But the worst case is when we have different clock generators working at different frequencies, and they may be totally independent. And that case allows to optimize every component in the best way, but the data transfers are a little bit risky, okay, because we don't have any time instance in which we know that the clock edges can be aligned. So the way to solve this unpredictability in time is by introducing handshakes in the same way as it is done in synchronous circuits. Okay? So we don't know when data will arrive, but we will include some signal, which is probably called the valid signal, that indicates when data will be valid at the receiver side. And the same way, we need a bidirectional communication, the acknowledged signal that will indicate to the sender that the data has been captured. Okay? This is very nice. Theoretically, we have two different clocks here, but the problem here is metastability, as one of the audience mentioned last week. So what happens there? So if you know a little bit about the details of how a flip-flop works, we have a window of protection that is saying, okay, if you want to send data to a flip-flop, this data should be stable sometime before and after the clock edge arrives. And this determines what is called the setup and hold time in a flip-flop. If the data arrives within that window, then the behavior you may expect on the Q signal is somehow non-deterministic. So basically this means that for a certain amount of time, this signal will be in some intermediate voltage that may be misinterpreted by the logic that is reading that signal. So we need some time to let the flip-flop stabilize, to resolve the metastability. So basically an illustration is like this, right? So typically we have a stable state, which is the logic 0, the logic 1. When we want to change state, we need to give energy to the system just to move maybe from the 0 to the 1, but maybe at some point the value stays there on the top of the mountain without saying, well, or deciding whether to go to the 0 or to the 1, okay? And theoretically, it could be here for infinite time. In practice, it doesn't happen because, I mean, the circuit has thermal noise, many things, and sooner or later, this ball will fall to one side or the other. But we don't know how long it will take to resolve, okay? So we need some time reference to say, when can we read that signal that has been in a stable for a certain time? And then the typical concept that it's introduced when dealing with metastability is what is called the mean time between failures. So, and there is some equation here that indicates how reliable it is to read a signal after a certain time. So mean time between failures says what is the probability, or it's the inverse of what is the probability that I have a failure, that metastability has not been resolved in a certain time, after waiting a certain time. And for this value to be good, we want the mean time between failures to be a high value, okay, of the order of years, centuries. So that means that in a century, for example, we will not have any fault. And that depends on the frequency of the clock of the data. If they have a high frequency, this is bad. It depends on the window of metastability, the setup hole window. If that window is big, that is bad. It depends on some technological constraints, but it mainly depends exponentially on the resolution time. So that means that if we give long time to resolve, then the probability to be a metastable is very, very low. Okay? So we need to give time. And to give time in a system means give several cycles. And how these cycles are determined? By the number of flip-flops you put just triggered by the same clock in reading the metastable signal. And this is a typical solution to solve metastability, to put a synchronizer, which a synchronizer means a chain of flip-flops. The more flip-flops we have, the more time we give to resolve metastability. And here's some typical example. Say, well, if you read the signal after one flip-flop, maybe we will have a failure every 15 minutes on average. But if you put 2 flip-flops, it will be several days. If we put 3 flip-flops, it will be several years. So the rule of thumb today is to put 3, 4 flip-flops in the current technologies, just to read this reliably. So that's the solution. We have the handshake signals, and now we put synchronizers on these control signals that determine what is the validity and the acknowledge of the data. Okay? That's a simple solution, but it has a problem that it's the throughput. So each time we want to send data, we need to wait for 3, 6, maybe 7, 8 cycles to send new data again. Okay? So that has a very bad impact on throughput. So there is another typical solution that is used, is putting asynchronous FIFOs. So this is typically a queue. The peculiarity is that in this queue we have 2 clocks, one clock to write, another clock to read. That is the clock from the sender, the clock from the receiver. This is typically implemented as a circular buffer with 2 pointers, one to read, the other to write, and the synchronizers are hidden here in the FIFO control. There is also typically some tricky encoding on the pointers. They use gray encoding. What is gray encoding? Basically, it's the value of the address of the pointer that goes from one to the next only changes in 1 bit. Okay? The good thing here is that the handshake only takes 1 cycle for the sender and 1 cycle for the receiver, okay? But the latency inside the queue may be 3 or 4 cycles at the minimum. What is the impact of that? Well, the latency can be a few cycles, but the throughput in writing and reading, it's 1. You can do 1 per cycle, okay? You have latency, but you can keep a high throughput. And that's a typical solution that it's done. When I mentioned these bridges here, the clock domain crossing, so typically they are implemented using asynchronous FIFOs and keeping this throughput as high as possible. Okay? Of course, if all the domains are asynchronous, then you don't have the metastability problem because you have the handshakes that avoid this indeterminacy in aligning the edges of the clocks that go into every component. Okay? So now we know a little bit synchronous, a little bit of asynchronous. There have been 2 worlds. The synchronous world has been dominating for many years, but meanwhile there was a small community of people still doing asynchronous circuits, almost forgotten from the world. So they had their own conference, very few people. Every year they were meeting and doing some exotic things with asynchronous circuits, still resisting there, but not many people paying attention to what they were doing. What happened at the end, so let me give a message in a discussion I had many years ago, or 9 years ago, with Mike Kishinevsky in Intel, and we were discussing with Bill Grundman. He is one of, he was the CAD director in Intel. He was also the technical director for CAD technology on the Alpha microprocessor project. And when designing complex systems, he was saying, well, when we envision a complex system, initially, we don't think about the clocks. We just talk about functional units, memories, register files, and sending messages among them. And implicitly, this is asynchronous, because it's message passing and all these things. It is when we go into the implementation details, when we start thinking about finite state machines, registers, clocks, and the cycles appear. But initially, the concepts are asynchronous, okay? And that made us think a little bit on how we could combine these 2 ideas. We have 2 worlds, so we had 2 worlds, the asynchronous and synchronous. Both have advantages and disadvantages. Synchronous was dominating, but what is the advantage of asynchronous? The advantage of asynchronous is the modularity in time. You have a system, you substitute one component by another. As long as you meet the handshake protocol, everything works. May have different performance, better or worse, but everything works. The problem is that the asynchronous circuits are hard to synthesize and analyze, mostly because of this time unpredictability. In the synchronous world is the opposite. So synchronous circuits are somehow, I would say, easy to analyze and synthesize, and there is a lot of CAD support for that. But they are not very modular in terms that they are rigid. If you change the timing of one of the components, you have to change the timing of the neighbors. So people started making efforts in trying to mix these two worlds. From the asynchronous world, there were attempts to make elasticity synchronous. And, for example, the synchronous emulation of asynchronous circuits was proposed, and later the synchronous handshake circuits. On the other hand, in the synchronous world, a new concept appeared, which is latency insensitive design by Carloni, Macmillan, San Giovanni, Vincentelli. And the idea was to also make time elastic, but discretize the multiples of cycles. In the middle, there was some effort by some of my colleagues and myself in proposing the idea of desynchronization, which basically meant that you can move from synchronous to asynchronous and vice versa in more or less an automatic way. These are different flavors of the same concepts. And then we proposed to talk about the concept of elastic circuits in a generic way, in which the fact of being synchronous or asynchronous is just an implementation detail. Sometimes an important detail, but it's just an implementation issue. So let me talk about different flavors of elasticity. And the first one is no elasticity. These boxes represent cycles. Okay, let's assume that we have a functional unit like an adder, and at every cycle we do an addition and we deliver a result. 2 plus 1 is 3, 4 plus 0 is 4, and so on and so forth. So these are the rigid systems. When we go into asynchronous systems, what we see is that we can shrink or stretch the cycle period and adapt to the operating conditions to the operands. Okay? So we cannot claim that we have a fixed cycle period. This may change. Now we are going to propose a different type of elasticity, which is synchronous, so it's still cycle-based, fixed frequency, but then we have unpredictability in when we deliver the data. So we have cycles in which we deliver results, but we also have some empty cycles. Basically, we call them bubbles. So this is an elasticity, but still synchronous. And why do we need synchronous elasticity? So it's a discrete elasticity, still cycle-based, but you can change the number of cycles. And there are many situations in the systems in which this happens. For example, in arithmetic, you can have, for example, short and long additions depending on the size of the operands or on the carry propagation, right? In floating point units, for example, it's not the same multiplying two numbers or multiplying a number by 0, okay? One of them you can do much faster than the other. The cache latency, so if you have a miss or a hit, you have a different latency. Even if you have a hit in the cache memory, the latency may be different if it's going to address the previous line or some other line that is in the cache. The latency is different. If you go to a system with bus arbitration, okay, when a request will be granted, it may take different number of cycles depending on the traffic on the bus, right? Latencies on a network on chip and many other situations. So we have dynamic latencies while the circuit is running. But even at design time, the elasticity may be interesting. So in today's systems, if you want to transfer that data from one corner of the chip to the other corner, it may take several cycles, maybe even 10 cycles. So the wires are slow, they are long. And what designers do sometimes is to do pipelining, to put several flip-flops there just to shorten the cycle period, take several cycles. But imagine that 2 weeks before the tape out, you realize that one of these wires is too long And then you would like to put another register there. But then it will change the timing, the number of transferring cycles, right? If you have an elastic system, you just put there a register with empty data, and then, if it is elastic, the functionality of the system will not change. It may change the performance, but not the functionality, okay? That's even a solution that you can use at design time just to optimize the system. And elasticity is not something totally new. I mean, many systems have been designed elastic in the past. And specifically, if you look at the protocols of the buses, they are elastic. So you see, for example, a clock, but for example, you see typically pairs of handshake signals, the valid and ready, and so on and so forth, right? But now what we are trying to do is just to formalize these concepts to apply them automatically in system-level design. So let's go into details on how to implement elasticity. Let's design systems with synchronous elasticity. And let's take this example. Let's take this long communication with long wires in which we have a slow transmission. So in typical synchronous design, to avoid a long cycle period, this is solved by pipelining. Okay, you put flip-flops there. And in my pictures, you will not see the clock signal. It's there implicitly, just to avoid complexity in the pictures, but we assume that all of them have a global clock. Okay? The problem with this pipeline communication is, how about if the sender does not always send valid data? And we don't know when this will happen. It's unpredictable. Okay? For example, and this is shown by this empty space here, the bubble means no valid data. So how does the receiver know that this data is valid or not? And here is where we introduce one of the handshake signals, which is the valid signal. It's one bit that is basically emitted by the sender and indicating to the receiver that you shouldn't pay attention to this data. You shouldn't do any computation. Okay, now we have the dual problem. What happens if the receiver is not always ready? So maybe this guy here is sleeping or doing some complex operation, and it will take some time to, or it's not capable of swallowing the data that is coming. Okay, how to solve that? Then we put the stop signal. It's a bidirectional signal that goes on the other way around. And this is the enable signal for this flip-flop. It indicates, so if we think about the complement of this signal, so the signal will be valid if it is valid and it's not a stop, so this will be enabled. It will be disabled when the previous is a stop and has valid data. And for example, if the stop is 0, then no problem, the pipeline will work, all of them will be enabled. These zeros here will be ones here, so all of them will be enabled. But if it says a stop here, then this stop will propagate until we find the bubble. So in the next cycle, we will move data one step forward. Okay, this stop will propagate backwards, and we will move data one step forward, and this stop will propagate until it reaches the sender, and we say, okay, stop sending data because the pipeline is full, and we cannot swallow data here at the receiver side. Okay, when the stop, and this phenomenon is called the back pressure in system design. When the stop signal becomes 0, then all of them will be released, and the data will be able to be propagated. Okay, that's not a problem. It looks like an interesting idea, except for the fact that if we put a stop here, one now, it will have to be propagated to the previous stage, and this will be a long combinational path. And this is contradictory with what we did before, because precisely we pipeline all this path here because it was very long and we wanted a short cycle period. So we cannot adopt a solution that requires long combinational path going in the backward direction. Okay, so we have to solve that. And one of the solutions was proposed by Luca Carloni in latency-sensitive systems using relay stations. The idea is that for every stage in the pipeline, we have double storage. So we have an auxiliary flip-flop or register just to store the incoming data that we cannot deliver to the next. The thing works as follows. So every stage has a main register, an auxiliary register. And in normal operation, we only use the main registers. Okay? So if the pipeline is fluent and everybody is working, so the receiver is operating, the sender is sending data every cycle, so we only use the main registers as in a normal pipeline. The problem comes when the receiver has the stop signal, so it's stopping the pipeline. Okay? So how does it work? Then the incoming data is stored in the auxiliary register, and then this stop signal is propagated one cycle later to the previous stage, but only one stage. So the back pressure, instead of going for the full pipeline, it goes stage by stage every cycle. And then this incoming data is stored here, and then this is propagated one stage backwards, the back pressure, and the incoming data is stored here, and then this is propagated to the sender. Okay? Now, when the receiver is able to receive more data, then this data is delivered in the same order as it was sent by the sender. Okay? And the order is recovered, and then we go to the normal operation. So the interesting idea here is that basically we need this double storage capability just to propagate the back pressure cycle by cycle without having long combinational paths. So what do we have? Let's look for another solution now, different from the one we saw before. So typically when we pipeline, we put flip-flops, and these tokens here indicate that these flip-flops have valid data, and the separation between flip-flops is one cycle. Okay? But we need double storage. And in fact, if you will remember how the flip-flops are designed, flip-flops are pairs of latches, master-slave latches. Okay? And at every half cycle, we send from master to slave, and the other half cycle, we send from a slave to master. This HL here indicate the high and low phase of every latch. They work with complementary phases of the clock. Okay? So, in fact, we have double storage here, because we have two latches, and in principle, we could store two values. But the problem is that flip-flops are not designed like that because they share the same clock. So basically, this situation here of having two data on the same flip-flop is not possible because they have the same clock working with complementary phases. Well, but we could just make a small change here and say, okay, let's make the master and the slave latches independent. We separate them and we put different control, different enabled signals. And with that, we can achieve the double storage, okay? So, and this is a scheme that is proposed to do this pipelining. So let me explain this. So basically, these are latches. The two different blue colors indicate that half of them work with a high phase, half of them work with a low phase of the same clock. The clock is not shown here. It's implicit. And we are showing here the enabled signal, also some of them in the high phase, some of them in the low phase. And here is the control for the back pressure. So these are latches, and when they have a token, means that there is a 1, there is a forward control for the valid signal, a backward control for the stop signal. And the normal operation is, well, this is one of the stages that we will extract away later. So the normal operation is that at every half cycle, data is moved, as in synchronous design. So this is the normal operation, when we have valid data here and non-stop here. Now, let's see how the back pressure works here. So let's assume that the valid signal is 0. You will see that the control is just removing all these valid signals, okay? And at the end, there will be a 0 at the receiver, indicating that you don't have valid data. Now let's assume that, let's go to another scenario in which we have valid data, so the sender will start sending valid data at every cycle, and the stop signal will be 1 saying the receiver is not allowed to receive data. And we will see how this control will propagate. So you see that the valid signals will become 1 until the pipeline is full, and when arriving at this situation in which we cannot send data because the receiver is in the stop status, then we will see that the back pressure is propagated cycle by cycle. The stop signal is activated until it reaches the sender. Okay, so that means the pipeline is full, all the latches have data, and the sender is not allowed to send more data because the back pressure has been propagated through this. Okay, I will not go into the details of this logic, what it means, but basically we have a valid data in a latch when there is valid data from the previous stage, or we have valid data in the current stage and the following is stopped. So that's the way we implement that, right? This is a very simple logic. You can look at the details. There are several papers written for that. So once the stop signal becomes 0, then we start sending data from the pipeline to the receiver, and then you see that the back pressure is propagated backwards, so it is released, until it indicates to the sender, now you can send data because you are not stopped any longer. Okay. So this small block that we sent before, okay, for the valid stop management, we will abstract away, we'll put this black box, or yellow box if you prefer, we call it VS, and now we will going to play with different VS components to do a few more complex things. So for example, we can have any arbitrary net list in the data path, okay? We can have forks and joins like others, whatever. This is not combinational logic, this is the control for the combinational logic that will be on top of that. So in fact, all these VS components generate the enable signals for the latches that are in the data path, and here you have any arbitrary structure. So let's look at the details of some of these forks and joins, for example. Imagine that we have an elastic system in which we have another that has 2 inputs, 1 output, okay? And here we have the VS components that we saw before to deliver the enable signals for the latches, okay? And here we have some logic that performs a handshaking for these 2 inputs and 1 output. Basically, the way it works is as follows. So some of the data will arrive first, and not necessarily simultaneously, because this is not longer synchronous, it's elastic, okay? At this point, since the other data is not available, we will send a stop signal backwards to this sender, because this will have to wait for some time, so we don't want to overwrite. We'll have to stop until the other one arrives, and when both are valid, then we will be able to deliver the result of the addition to the following latch, okay? And this will not be stopped any longer. So we see this logic, basically what we say is that we will send a valid signal when both inputs, V1 and V2, both are valid, okay? And if one of them is valid, the other not, then we will send a stop signal for the one who is valid, just avoiding to overwrite the value that is there waiting, okay? So this is the type of handshake we have to do. We can also have forks, for example. We are not showing the latches here just for simplicity, but imagine that we have some valid data here that has to be delivered to 2 different channels, okay? So the way it is done is when these 2 channels are released, are available, so we simply send the token to both of them, and that's it. In that particular case, we call this a lazy fork, because the 2 tokens are delivered when the 2 output channels are free, okay? If one of them is busy, then we will wait for, until both are free. But we can have another version, which is the eager fork, which is more efficient. That indicates, okay, we can have valid data here, and maybe one of the output channels is stopped, but still the other is available. So this logic here basically will make that this token will be sent to the available channel, the one that is not busy, and once the other one is not stopped, and then it will send the token to the other channel. So this logic here is more complex. It basically has a flip-flop also for every output channel. It's a bit just to remember if the token was sent or not, okay? And when all of them are sent, then you send the acknowledgement to the previous, and that's it. And the more important, you can have variable latency units. So we can have here, for example, another that may take 0, 1, 2, 3 cycles, or floating point unit, or maybe some algorithm that is implemented by a sequential circuit, like calculating the greatest common divisor of two numbers. And by putting some handshake on these units, for example, these 3 signals indicate go is start operating. It will indicate when it is done, and the clear is just to restart for the next operation. There can be many handshakes here, different flavors. But here we can have functional units with arbitrary number of cycles. And the most important thing here is that if someday you have a better implementation of this algorithm here, you just substitute one block by another, the whole system will keep working without requiring to make any change to the rest of the logic. You may change the performance, maybe better, maybe worse, but you will not change the functionality. Functionality will remain the same. This is a very important concept. So let me talk a little bit about design automation. So all these concepts may be nice, but we would like to have tools to do this automatically, right? So they are not commercial yet, so the level of academia, but we know how to do these type of things. And the idea is, what is the best automation? I mean, people are used to design synchronous circuits. There are plenty of tools to support that. So imagine that you do the design, your classical style, synchronous circuit. The only thing you have to do is just take your flip-flops and split into pairs of latches, master slave, and put the control there. Okay? So one of them will have valid data, the other will have bubbles, and you will put control there. Even you can put bubbles arbitrarily everywhere you need. For example, you want to shorten the cycle time of these long wires, for example, you can put bubbles here, and as long as you don't put valid data, the functionality of the system remains the same. So there is no problem in that. Even you can distribute your latches maybe evenly across your long wires just to do a better pipelining and shorten the cycle period. All this can be done automatically, right? And the important thing, the behavioral equivalence is preserved. So one of the exercises that was done by a student who did a master thesis, and it was co-advised by Gérard and myself, was on elastic Esterel, and we saw this example before, right, the Abro circuit. So just to show this very simple example how you can make Esterel elastic, and this affects basically on the implementation phase, on the synthesis phase. So from Esterel you can just simply generate a netlist that will come from this syntax-directed translation plus optimization of the Esterel circuit. And here, just to transform it in elastic, the only thing we have to do is just split the flip-flops into pairs of latches, okay? And then for every signal that we have in the system, basically we need the pair of handshake signals, the valid stop signals that indicate or implement the elasticity of these signals, for example, valid stop for A, R, and B, and O. And then we have the elastic control layer. So here we will have those VS components with the forks and joins or whatever you need. And finally, this elastic control will generate the enable signals for the master-slave latches. Okay? And in this automatic way, we have transformed something that was rigid into something that is elastic and can communicate with other elastic components through these handshake components. Okay? So let me give also another view of what these concepts we are talking about. So in a rigid circuit, basically, what you have is a set of registers that are pipeline, and we assume that every register has valid data. And cycle by cycle, we are moving this across the pipeline. In elastic systems, we can talk maybe about two concepts. One is the logic cycle, the microarchitectural cycle, and the other is the circuit cycle. And the microarchitectural cycle may be implemented by some microcycles, circuit cycles. It's like saying, okay, in a microprocessor, we can have instructions that are executed one every cycle. But maybe inside that cycle, we have microprogramming with microcycles. Okay? So the observable cycles are the same. And which are the observable cycles? The observable cycles are the ones in which they have the valid signal at 1. when the valid signal is 0, then that it's not a valid cycle. Another paradigm to do elastic circuits, synchronous elastic circuits, comes from the asynchronous community. And this is the same picture I showed last week for the syntax-directed translation generating handshake components. In fact, this is an asynchronous circuit, the first version of that, implementing the Euclid's algorithm for calculate the greatest common divisor. And in the same way we saw before, we can substitute these handshake components by synchronous handshake components. And these channels have request acknowledge signals. If you want to be synchronous, you can call valid to stop. And the sequential elements here are triggered by a common clock. So by just having the same structure and make it elastic, you can incorporate synchronous elasticity with this paradigm. Even you can be more general. And remember, we have split these flip-flops into pairs of master-slave latches. In fact, the pair of master-slave latch is a small queue, a small FIFO of 2 slots. You can generalize that by putting FIFOs as many elements as you want, maybe for performance reasons, okay? And then this can be generalized into other concepts like, for example, bounded data flow networks. And the idea here is the same. As long as you have valid data, you do progress. When you don't have valid data, you wait, and the observable behavior is the same, okay? In fact, that is the concept of behavioral equivalence. In a synchronous circuit, we have a clock, and this D represents data. At every cycle, we see different values in one of the registers of the system, A, B, C, D, and so on and so forth. When we incorporate elasticity, we have data plus the valid signal, okay? And only the cycles in which the valid signal is 1 are the meaningful cycles. The others should be ignored. So if we would remove the cycles with the 0 valid, then we will see that the trace of values here and here would be the same. So why are we doing that? Well, because for convenience, just for elasticity in the communication. Maybe this has more cycles, but the cycle period is smaller, which is good, okay? So that's the type of equivalence that we are preserving. Let me talk a little bit about early evaluation. And this is also an interesting idea for performance reasons. So let's imagine that we have an elastic block. This is a multiplier, and these are the input latches of FIFOs. The typical operation in an elastic mode is, okay, we have some input data. We have to wait to have available data in both inputs just to do an operation. So when we have another data here, 5 times 3, we will do an operation and we will send the result to the next stage, okay? And here we may have another one that arrives, 2 times 3, we will deliver a 6, and so on and so forth. Now imagine that in the input channel above, we have a 0, okay? And the right thing to do, the conventional thing to do in an elastic system is to wait for the next operand and then do the multiplication and send the result. But hey, there's something special here. That's a 0. So do I need to wait for the next operand to deliver the result? Doesn't matter what I get, I will have to deliver a 0. But on the other hand, I know that the other operand will come because somebody is generating. So I can improve the performance by saying, okay, I will send a 0 because I already know the result, but I must be prepared for the next operand to come. So what I will generate is, instead of a token, something we call an anti-token. Something say, you should cancel the next value. So when the next value arrives, we know that we have to disregard it. So a token and an anti-token will meet, and the sum of token and anti-token is nothing. They destroy, they cancel each other. And a typical example here is in multiplexers. That's the best example that we have very often in circuits. This is the typical example of, for example, in a microprocessor, when we have to calculate the next program counter, usually we have 2 options. One is the program counter plus 4, that means the next instruction, or it's the target of a branch. Okay, we do a branch and we may have another. So, and we have a multiplexer that indicates whether, depending on whether we take a branch or not, we will select this one or this one. So imagine that, for certain reasons, these two tokens arrive, and this token arrives with the information saying, I don't have to take a branch, okay? And the PC+4 is here, and the other is still being computed in the ALU. So what we can do is just to take the decision, because we have sufficient data for that. Okay, so we send the token, but we will send also an anti-token to cancel the other that will be coming from some functional unit. And this anti-token can be passive or active. It can be waiting, or we can send them backward just to meet the other token. The way to implement that is very simple. So basically in the control, remember that we have those small control circuits with a valid stop signal. So we just have to duplicate this control, but in the opposite direction, just moving anti-tokens. And we have the valid and stop signal for the anti-tokens going into the opposite direction. And they communicate these two circuits, saying, well, when you have a token here and a token here, one is a positive token, the other is a negative token, they will disappear. Okay? That's the way it can be done. And just some details. This is the way to implement it. This was the same logic we saw before, the VS logic. And we just, and you see that the dual one is exactly the same, but duplicated and going into the opposite direction. And they also have some small logic to detect when both have a token, anti-token, and they disappear. Okay? And this just details on how you can implement forks and joins with the positive and negative tokens. They were pretty tricky circuits, but they were formally verified by formal verification tools, and they work correctly. So one of the things we can do now with early evaluation is to adapt the functional units for the average performance. Imagine that we have a functional unit f that receives some inputs, produces some outputs. But depending on the inputs, the computation of f could be fast. Depending on the inputs, it could be slow. I mean, you could optimize for every case. And for example, you could redesign f in a way that for certain cases you do a complex operation, for certain cases you can do a fast operation, and maybe some control circuit will detect when the slow or fast case should be selected. Okay, so we can put this multiplexer with early evaluation, which basically means, okay, you make them run concurrently for the slow and fast case, and if you know that this is a fast case, and this will take maybe one cycle, this may take 3 cycles, elastic cycles, okay, then you deliver the result, and in case you use the fast option, then you will send an anti-token to the slow fragment of the function, and will cancel the other operation. Okay, in this way you can speed up. So let me explain an experiment that was done internally in Intel with some of my colleagues. They implemented a Kavak decoder. This is for string compression. Basically, it's used for video compression. And I will not go into the details. So they have different components here. And they did some profiling to check what type of operations were more frequent in that decoder. And they realized that one of the operations was the typical one that was the most frequent, and then there were other operations that were rarely executed. And the problem here is that when you design this component, for example, the critical path is determined mostly by those operations that are not executed very often. So what they did is just to optimize for the most often operation, and they did one circuit, the read 1 and read 2, for the most frequent operation. That was a fast combinational logic, while the other for read 1 and read 2 at the bottom was for the most exotic operations, the not so frequent operations. It will take more cycles, okay? And they did that optimization, and then they start playing with the synthesis tools, trying to optimize for area or performance. And this is a little bit summarizes the design space. As you know, in synthesis tools, if you want to push for performance, then the synthesis tools will start duplicating logic and making gates bigger and all these things, right? So the area of the circuit will grow, but also the cycle period will shrink, okay? If you want to go for area, then you can reduce area at the expense of increasing the cycle time. So in the original circuit, the one that came from the specification, that was the exploration space. When they optimize and they try different options for area and performance, that was the exploration space. And what we see is that if performance is not critical, then they were using more area to get similar cycle period. More area because they duplicated some logic for the fast and the slow case, right? So it's not worthwhile to do this for here. But when they wanted to push for performance, that is the average performance they were acquiring. So they could reduce the cycle period much more, of course at the expense of area, but you see that there was a lot of room for optimization. And that was possible by using elastic circuits and using tokens and anti-tokens for early evaluation and optimizing for the average performance and not for the worst case. And I would like to finish now. It's time to finish. So conclusions. So the rigid systems preserve timing equivalence, and what we see is that at every cycle we have valid data. It's cycle by cycle, we're delivering one data every cycle. When we introduce elasticity, here we have much more flexibility to optimize for area performance. And why? We are using the fact that we can use bubbles. So we can do pipelining, putting bubbles in the strategic places to reduce the cycle period, but we can optimize for performance also using the anti-tokens, right? We can do things in parallel, take the fastest result, cancel the other one, and all these things. So, and I didn't show you here, but we have been working also on how to pipeline systems in an automatic way. By doing these transformations and using techniques like retiming, exploration algorithms based on linear programming, dynamic programming, and all these things, we could move from systems that are basically sequential into pipeline systems, pipeline microprocessors. So I think that there are new opportunities here to do high-level synthesis and automatic pipelining based on these elastic transformations. If you want to read a little bit, I'm just making a little bit of publicity of a paper that we published some time ago. In this paper, we tried to unify a lot of knowledge from a synchronous domain and from synchronous domain and create this concept of elastic circuits in which most of the theory is the same. As I mentioned at the beginning, the fact of having a clock or not is just an implementation detail. You can be synchronous or asynchronous, in both cases, elastic. Okay? And thank you. That concludes my talk.